Hello everyone. In today's video, we'll take a look at how a stack data structure works and how to implement it in the C programming language using an array. A stack is a data structure that follows the LIFO principle, which stands for last in, first out. This means that the last element added is the first one to be removed. You can think of it like a stack of plates. When you pile them up, you start from the bottom and build upward. When you need a plate, you take the one from the top, not the one at the bottom. A stack has two main operations: push, which inserts an element at the top of the stack, and pop, which removes the last element that was added. There are also auxiliary methods such as isEmpty, which checks whether the stack is empty, and isFull, which checks if the stack has reached its maximum capacity. Stacks are commonly used in tasks such as function calls, expression evaluation, backtracking algorithms, and many other areas where reversing or tracking previous states is necessary. The process begins in the main function, where we declare an integer variable named size. This variable is stored in the stack memory segment of our program. At the moment of declaration, it contains a garbage value. Let's assume that its memory address is Xerox 4444 for illustrative purposes. We then prompt the user to enter the desired size of the stack. For this explanation, let's assume the user enters the number 5. Consequently, the memory at address Xerox 4444 is updated to store the value 5. Next, we declare a pointer named stack, which is intended to store the address of a stack structure that will be dynamically created in the heap memory. Initially, it is uninitialized. Later, we assign to it the return value of the initialize function, which is responsible for allocating and setting up the structure. Inside the initialize function, a new local variable named newStack is declared. This is also a pointer to a stack structure, and like all local variables, it is stored in the stack memory. This variable is temporary and will be used to construct and return the new stack instance. At this point, we allocate memory in the heap using the malloc function. We request enough space for one stack structure. The memory allocated is contiguous and large enough to hold all the fields of the stack struct. If the allocation is successful, newStack now stores the memory address of the first byte of this new structure in the heap. It's important to check whether malloc returned null, which would indicate a failure in memory allocation. If this happens, we print an error message and return null. We then allocate memory for the R field of the structure. This field is intended to store the elements of the stack. This memory is also located in the heap. The RR field in the structure is updated to point to the first element of this new array. That means one of the fields of the structure now contains the address of a separate block of memory, which is also in the heap. Notice that we use calloc instead of malloc to not only allocate memory for size integers, but also to automatically initialize all of them to 0. As before, we validate the memory allocation. If calloc fails, we print an error, and also free the previously allocated newStack structure to prevent memory leaks. A stack structure without a working internal array is useless, so we must clean up properly before exiting. We now initialize the remaining fields of the stack structure. Max stores the maximum number of elements that can be pushed onto the stack. It is set to the user-provided size. Top represents the index of the current top element in the stack. Since the stack is empty at this point, top is initialized to -1. The function finally returns the pointer newStack to the caller, which is main. However, since newStack is a local variable, it disappears once the function finishes execution. Fortunately, the pointer value it held is returned, and in main, it is assigned to the stack pointer. So now, stack points to the heap allocated structure and remains alive as long as we keep using it. The push method is responsible for inserting a new element into the stack. It does this by first increasing the value of the top index, which keeps track of the current position at the top of the stack. By incrementing top, the method moves to the next available position in the internal array. Then, it assigns the given integer to that position, effectively placing the new element on top of the stack. This simulates the behavior of stacking one item over another in a last-in, first-out manner. The pop method, in contrast, is used to remove and return the element that is currently at the top of the stack. It starts by accessing the value located at the top index of the array and stores it in a temporary variable called deleted. This represents the element that is about to be removed. After retrieving the value, it decrements the top index to reflect that the top element has been removed from the stack. Finally, it returns the stored value, completing the process of removing the most recently added element. This maintains the LIFO structure, where the last element inserted is always the first one to be removed. As mentioned at the beginning of this video, there are two auxiliary methods that are especially useful when working with a stack. The first one, isFull, checks whether the stack is full. This is determined by verifying if the value of top is greater than or equal to max minus 1. We use max minus 1 instead of max, because arrays in C are zero-indexed, meaning they start at index 0 and go up to n-1. On the other hand, the isEmpty method checks whether the stack is empty. This condition is true when the value of top is equal to -1, indicating that there are no elements currently stored in the array. These two methods are particularly useful when performing push or pop operations. For instance, before pushing a new element onto the stack, you should check that the stack is not full. This can be done using the negation of the isFull method. Similarly, before popping an element from the stack, you should verify that there is at least one element present, which you can ensure by checking isEmpty method. So now you know how to implement this data structure in C. Just remember that this version is based on arrays, which means it has a fixed size and can't grow dynamically. In an upcoming video, we'll cover how to build it using nodes, which makes it much more flexible. Thanks for watching. If you found this helpful, don't forget to like the video, subscribe to the channel, and keep practicing. Understanding these concepts is a big step toward mastering data structures in programming. See you in the next one.